So I'm going to kind of work through this criteria for invertibility, which is that a matrix is going to be invertible if its columns are linearly independent. So let's demonstrate the opposite of that. You guys with me? So dependent columns is going to imply not invertible. Okay. So let me just suppose I have a matrix A, which is going to be square so that we can even talk about invertibility. You guys with me on that? Okay. So I have a matrix A that's n by n. That means that my matrix has columns. So I'm going to talk about this collection of columns, this set of columns. So I've got columns C1 through Cn. You guys with me on that? Okay, so let's suppose we had A with these columns, and the C's are linearly dependent. You guys with me on this? Okay. So that means what? What does it mean for vectors to be linearly dependent?
You can find scalars such that they get to zero.
Yeah, there's a collection of scalars, right? So I kept this for a reason. So a collection or a set of vectors is linearly dependent if there are a set of scalars that are not all zero that add to zero, right? Okay, so if I have linearly dependent columns, then there's that same collection of scalars, right? So we're going to make that collection of scalars A1 through AN. I need to back up a word. So then there exist these scalars with A1, C1 added yada yada to AN, CN equals the zero vector. Yes? You guys all with me on this? Okay. This sum happens to be the exact same thing you get by taking A and multiplying it by what? We're going to multiply by 0 in a second. So how do I see all these A's times C out of taking A and multiplying it by a vector? So remember, the C's are the columns, right?
Yes.
And when you multiply a matrix by a vector, right? You've got your matrix, you've got your vectors. Pick these vectors up and drop them on, right? So the column multiplication picture tells you that that first scalar up here is going to get dropped onto that first column all the way down, right?
Yeah.
So this A1, C1 comes from me taking this matrix A and multiplying it by a vector that starts with A1.
All the way to AN, I'm guessing?
Yep, and then in order to get AN times the nth column, AN has to be the last thing. You guys see that? So that sum is made by taking this matrix and multiplying it by the vector A1 through AN. You guys see that? That is the column multiplication picture.
Yep.
Okay. Now, this tells me that the vector A1 through AN got mapped to the zero vector. You guys see that?
Yes.
So, functionally, right, I have my matrix A, and I know that this one dot A1 through AN went to one very specific place over here. It went over here to the 0 vector. This is not necessarily a problem. You see this? All I found out was that A times that thing gives me 0, right? So in the functional sense, A of this thing is 0. Who cares? Doesn't matter. Like, whatever. No problem. Like, sure, that's what functions do. They take stuff, turn it into other stuff. Okay, now, Ricky said earlier that it was A times 0. She's not wrong. So let me think about what A times 0 is, or A of the 0 vector over here. If you take the matrix A, and you multiply it by a vector full of zeros, what do you get? Yeah, you get the 0 vector. You have to. You can't get anything else. Yeah, see why? Because you're picking up this vector of zeros, twisting it sideways and dropping it onto whatever's in there, and it doesn't matter whatever's in there. This is actually interesting because this is always true. Right? When A is a matrix, and you multiply it by the 0 vector, you always get the 0 vector out. Nothing else. That's always what happens. For each and every matrix in this class, that will be true. It is an interesting thing, because there are very few math classes where I'm like, and all the way through the book, every function we talk about is going to map 0 to 0. Can you see that? So, what is the problem?
If you can't map the 0 vector back to the vector.
Yeah, you can't back out of this situation. In order to reverse it, you'd have to take the 0 vector to both places. That ain't going to happen. This thing just failed the horizontal line test for an inverse. I didn't really draw a horizontal line, but that's what happened. So what happened is it lost some information. What's really going on here is that any multiple of this A vector gets smashed. So it's acting like it's taking n space and crushing it by at least one dimension. Well, we're done. Can't back out of that. That's it. This is not invertible. So that gets us to linearly dependent columns imply that the matrix is not invertible. You guys see that? Okay. Now, the matrix is invertible implies the columns are linearly independent. Right? That's what we just did. So, linearly independent columns imply the matrix is invertible is the same line of reasoning. It's not often you get both. You guys know this word, if only?
Yep.
Okay, so that means that this implies that and this implies that. This is one of those rare cases where you're going to get both implications for free.
Cool. I like that.
Cool. Okay. Questions, things? You guys good with this?
Yep.
Does that help you do the thing you needed to do on the homework?
Yes.
The answer is yes, but the question is whether you know how it helps you.
Yeah.
It tells that we have a definition, but how do you actually go about it? Inverting the matrix.
Oh, how do you actually invert a matrix?
Yeah, because
I
we
have a
talked
chart.
about how it is invertible.
You want to see
Now,
my little
like, can we
list?
invert it?
Okay, so let me tell you. Let me see. What do I want to tell you?
Ooh, you want to see it? He's gonna tell us. So you switch change size.
I think what I want to tell you right now, just like on the second day or whatever, is that the way you invert a matrix is you go to Wolfram Alpha and you ask it.
What?
That's great.
Right?
Because I want to talk about how to calculate an inverse in a more specific way, but after we get a tool. Okay, let me give you the 2x2 inverse trick. Wait, you need a 3x3 inverse?
Yeah.
We got 3x3 inverses in our.
Yeah, just ask Wolfram Alpha.
Oh god. Okay.
Fine.
There is a longer procedure. I don't care if you know it today.
Okay.
That's so fine with me.
What?
I said that's so fine, just like looking up, I don't know, Wolfram
But if there's
right
like
now.
unknowns in it, you can plug unknowns into a calculator.
Ah.
I ran into that last night.
Okay.
So I had to do it by hand.
So,
Oh, no, I just-
it should be noted that sometimes the textbook will ask questions like, here is a matrix with some numbers in it. When does it fail to be invertible? And that is a slightly different question than you're asking.
Yeah, they asked it at 1.3.
Okay.
That's like that's conceptual question rather.
Yeah, so what you want to do in that case is think about this linear independence of columns. And if you're looking for where does it fail to be linearly independent, you're looking for linear dependency, right?
Yeah.
So force it. Make one of the columns the zero vector. Make one of the rows the zero vector. Make two of the columns identical, or make two of the columns add to the third one.
Okay.
Like, that's the kind of trick you're going to use. Same thing with rows. Questions on that? Okay, cool. I hope that